All right. It's been a while, but welcome back to the channel. We are continuing our journey on trying to review all the MCAT content review before we go on to the questions. Today, we're going to tackle solutions. I think it is the chapter 9 of the MCAT General Chemistry Review. We took a break for a long while, about 2 months, because, there were so many things, life happened. Let's talk about solutions. Do you know why cold packs, the instant cold packs and sweet tea works? Well, they do work because cold packs contains ammonium nitrate on one side and water on the other side. When you crush them together, the ammonium nitrate mixes with the water. And when the ammonium nitrate is dissolving in the water, the process takes in heat. So when the process takes in heat, when you use that Copax to touch onto your skin, you feel the difference or the heat leaving your skin. And the heat leaving your skin is given by the sensation of the coldness. That is how the cold packs works. Similar thing for the hot pack. And then sweet tea too, it is just a concentrated sugar solution and with a highly brewed tea that you put in water. It's the same thing. It works as it takes in heat from the environment to work. But since the heat that it takes is not as great as the instant cold packs, you do not really see that much of a difference when you stick cold tea or sweet tea onto your skin. Now, when we talk about solutions, what we do mean is that we take in one solvent or a solute and then we putting it in a solvent, like one substance and putting it in another substance. Essentially a mixture. So we could say that all solutions are mixtures. But what you should note is that not all mixtures are solution. So as you said, I have made point of some keywords. The first one that I said was a solute. Now a solute over here is the substance that we are dissolving, right? And they are usually in the tiny, the lesser quantity, depending on how you're trying to measure it. If it's in grams, it is of less grams than the solvent. And then the solvent, on the other hand, is the substance that we are dissolving the solute in. Dissolving the solute in, and it is usually in much greater quantity than the solute itself. So now that is the difference between a solute and then a solvent. And when a solute and a solvent combines, then we get what we call a solution, right? So solution. But then the book definition of a solution is a homogeneous mixture, right? A homogeneous mixture between a solute and a solvent. That would be a solution right there, homogeneous mixture between a solute and then a solvent. Now, this leads us to the types or the nature of solutions that we have. Since we have three states of matter, which is so nature of solutions, let's write the nature of solutions here. Since we have three states of matter, which is solid, liquid, and gas state, we can combine some of these things to form different solutions, right? Now we can have a solid, so a solid solution. Now, solid solutions are usually metal alloys. Like when we take a metal alloy like steel, which has a combination of carbon and then some other metals, that is a solid solution. And the end product is a solid. Now, we can have a solid liquid solution in which the liquid usually serves as a solvent. Those are so many things that we have in our everyday lives, and that is the general concept of a solution when somebody says it. Now we can have a solid gas mixture. Now, solids and gas usually do form a mixture, not a solution, because they don't really mix. On the other hand, we can have a liquid-liquid solution, either a liquid dissolving another liquid, like if we dissolve ethanol in water or methanol in ethanol. The solvent is the one that is in the excess after we are done dissolving it, and then the solute was the one that is in a small quantity. Now, if the solvent and then the solute are in equal quantities, when we mix them, like in the case of a liquid-liquid mixture or solid-solid mixture, then the solvent, it is going to be the one that is universally used as a solvent in that case. Like, let's say we are going to mix something in water. However way the mixture is, if there is a same quantity of solute, such as solvents, then the water is literally going to be our solvent. Now, once we are done with the nature of solutions, let's talk about something that we call solvation. Now, these words can be used interchangeably. Solvation, hydration, and dissolution. So these things can be used interchangeably, but the only difference is what substances are usually involved when we are doing it. Solvation comes in when we put a solid substance into a liquid or a water. Usually, we're going to use water as our solvent here because the MCAT focuses on aqueous solution, which is water as the solvent. So let's say we put our sodium, let's take our salt to be sodium chloride, right? NaCl. And then we put that sodium chloride in water. Now that is called solvation, right? That means the water molecules are going to attack the ionic bonds between the sodium and the chlorine molecules, will break them apart, and then it will be solvated, like it will be surrounded by the water molecules, and that will dissolve. So that is why it can be solvation. But sometimes, if water is not the aqueous solution, we use solvation and dissolution. If water is involved, then we use hydration, because water is gives you the hydration thing. So that is how solvation and hydration and dissolution work. But if you want the theoretical definition of solvation, it is the electrostatic, say the electrostatic force of attraction between the solute and the solvent particles. Like I said, let's say we have sodium chloride here, where we have like the sodium chloride, our big. Let me pause that. So let's say we have the sodium chloride over here. We put the sodium chloride in water. We are going to have the sodium being separated. So let's say the sodium is separated. Once the sodium is separated, we're going to have our H2O, which is the water. And then you know water is polar covalent. So the hydrogen here is partial positive, and then the oxygen here is partial negative. So the partial negative is going to be attracted to the positives of this charge. So you will see the oxygen molecules surrounding the sodium. Let me do it this way. The sodium ions like this. Partial negative, O, partial negative bonded to H2. Just like that. Surrounded all in the water. Now, this is called solvation or hydration, or sometimes dissolution. They are all interchangeable. But another thing that I want us to also look at is that when you put a substance into, or when you put a solute into a solvent, whether it is going to dissociate readily, that is like spontaneous dissociation, or whether it is not going to dissociate spontaneously depends on the Gibbs free energy of the entire solution. Now, why am I saying depends on the Gibbs free energy? From the previous chapter, we realized that the change in Gibbs free energy is equals to the enthalpy change, let's put a degree here, minus the temperature change in the entropy, right? Now, if Gibbs free energy, right, is less than 0, then it dissociates readily, like it is spontaneous dissociation. This one gives us spontaneous dissociation. And spontaneous dissociations occurs, or it is favored at lower temperatures. Lower temperatures. Now, why is it that when the change in Gibbs free energy is less than 0, it is spontaneous dissociation and then it occurs at a lower temperature? See, this is the change in the Gibbs free energy, right? And then over here is the enthalpy. That is the heat that we are, or the energy that we are getting from the environment. And then this over here, the entropy, it is the disorderness, like how disorderly we get. So this negative sign over here tells us everything, that the more disorderly we get, that means the Gibbs free, the entropy is bigger, because, as the disorder increases, the entropy gets bigger. The more entropy we get over here, that just means that we are going to have a bigger value over here. And then the bigger value over here, that means we're going to subtract it from whatever the enthalpy is, and then it is going to be less than 0. So when we get that, then we just know that the whole dissociation is going to occur spontaneously. Yes. And then I said, okay, at lower temperatures. Now you might say that there is a temperature here. So wouldn't it be that the bigger the temperature, the less, the more spontaneous it is going to be? But then when we talk about it, we have to look at a shift. We have to shift our way of thinking into thinking more about the Le-Chatelier's principle by considering temperature as, or heat as, a byproduct of the whole dissociation thing. So if we have that sodium chloride, like I said over here, I don't want to come here just yet. We have the sodium chloride, NaCl, dissociating to become the Na plus our Cl minus plus heat. That means we are giving heat into the environment, possibly. So that means that if we increase the heat output over here, then the equilibrium constant is going to shift to this side, making us produce more NaCl over here. And we producing more NaCl doesn't favor our reaction, because we want to produce more of this. But if we reduce the heat, that means more NaCl will have to dissociate to give us more heat. Is everything okay? What?
That's the second dick.
That means the NaCl over here would have to dissociate to give us more heat. So the less heat we put into the system, the more spontaneous it gets. That is why when the change in Gibbs free energy is less than 0, it is spontaneous and it occurs at a lower temperature. The same thing goes for the reverse, the reversibility of it. That means if the Gibbs free energy, the change in Gibbs free energy is bigger than 0, then it is non-spontaneous. And then it's favored at higher temperature. So favored at higher temperature. Solubility. Now, when we talk about solubility, all we're trying to say is that how much solute can you dissolve in a solvent at a given temperature? So solubility is just how much of a solute can be dissolved in its solvent, right, at a given temperature. That is solubility for you. So basically, when we have what is it called? When we have a solution, the solvent has a specific solubility. That means it can dissolve a certain amount of solute. And once that solute is rich, the point that once it dissolves its maximum amount of solute, we call that point. Oh, why is the name escaping me? Yes. So when it has dissolved the maximum amount of solute it can dissolve, we all know that at that point we call it that the solution is saturated. So saturated solution, right? Saturated solution. And then a saturated solution is just a solution that cannot dissolve any more of its solutes at that given temperature. A solution cannot dissolve any more of its solutes at the given temperature. Now, as you see, there is always given temperature over here because solubility depends on temperature. If you increase the temperature of the solution or of the solvent, you're going to dissolve more stuff into it. It happens in our everyday home. If you take a lot of sugar and you put it in cold water, at some point, the water cannot dissolve any more sugar. And whatever sugar that you put in is going to precipitate and crystallize at the bottom. But the moment you put that sugar solution on the stove and turn up the heat, you could throw in more um, sugar and then it would dissolve it. Now, we can also link to solubility to like Gibbs free energy and then all those, but they all depends on the same thing, like how readily a solution would dissolve more of its solutes. It just goes hand in hand with just the Gibbs free energy. If it's less than zero, it will spontaneously dissolve more of it. If not, it wouldn't dissolve more of it. But not everything dissociates easily. Like I use sodium chloride, for instance, over here, because when you put sodium chloride in water, it's just easily. But not everything does that. So if something doesn't dissociate so much easily, we call that sparingly soluble. We call that those substances sparingly soluble solutes. So these could be anything that don't dissociate or dissociates easily in the aqueous solution. So does not fully dissociates in the solution. So those are sparingly soluble stuff. And from here, from the solubility over here, let's tackle much more of aqueous solution. Now, when we talk about aqueous solution, all we just means is that water. Aqueous solution is just water solution. Now, what makes this good is that when you dissolve things in aqueous solution, you split the water and then you could form hydrogen ions or hydrozonium ions. But then most times you could form a hydrozonium complex when you dissolve it into like something that is electron, like a proton donor or electron pair acceptor. In other words, when you dissolve it in a Lewis base, you could form hydrozonium ions. And hydrozonium ions is just H3O. This one. You could put a plus here if you want. It's just a proton. But you barely see this in like proton just by itself in water. They are mostly always attached to some species. For example, if you dissolve acetate in water, CH3COOH in water, you form the acetic acid, which is CH3COO minus over here. See, you will lose these hydrogen ions, and then you just have your hydrozonium ions over here. Oh, so this H got deprotonated, and this one got protonated. Now, our next chapter is going to be acids and bases. So when we get there, this deprotonation and then the protonation, electron pair acceptor donor situation will make sense in the next chapter. Pause it. Good. So from here, from us considering aqueous solution, if we are considering that as our main sort of, solvent, if you're considering aqueous solution, which is water, to be our main type of solvent, it gives us 7 solubility rules. Now, this is where things get a little bit tricky, even for me, because memorizing the 7 solubility rules might not be too hard for some others. But the MCAT doesn't care whether you memorize all of them or you just know the facts. Now, the thing is that I would urge you to keep the first 2 in mind. So let's try to see how many of the solubility rules we can remember on top of our head. So the first solubility rules is that all ammonium, that is NH4 plus, ammonium salts, right? Like all salts containing ammonium and alkali metals. Now, the alkali metals are the group 1 metals on the periodic table. So all ammonium salts and alkali metals are soluble. That is assuming our solvent is aqueous solution. That is the first one that you need to put in mind. And then the second one is that all salts containing nitrates, so all salts containing nitrate is NO3 minus, right? Did I get it right? Yes, NO3 minus and acetate. And acetate, which is CH3COO minus, are soluble. Now, these 2 solubility rules are non-negotiable. You need to know this on top of your head on the MCAT. But if you want to go ahead and memorize all the other 7s, the next one that follows are the halides, right? That is the group 7 elements. The halides, which is chlorine minus, bromine minus, iodine minus. You see how I didn't bring fluorine here? Except fluorine minus, right? What did they do? They are also soluble. They are soluble. When you form the salt, all halides containing this are soluble. But also, if they form the salts with, so if they form the salts with these musketeers over here, which is silver 2 plus, lead 2 plus, and then mercury 2 plus. If they form the salts with this, then they are insoluble. Then it's insoluble. See, also all metal oxides are insoluble, except CaO, calcium oxide, barium oxide, and then I think strontium oxide is SRO, if I'm not mistaken. Let me see. Yes, strontium oxide. And then the other ones that you want to know is that for this one, which is the all metal oxides are insoluble except for these things, right? If the metal oxides are the alkali earth metals over here, and then ammonia that are forming the oxides like ammonium oxide, or when you put the alkali earth metals, that is hydrogen, helium, the lithium coming down, sodium coming down, that chain, when you do it like that, then they are soluble. One thing you should put in mind is that these alkali metals, whoever they form their bonds with or whoever they do it with, they are always soluble. But there, and then the salts that are containing nitrates and then acetate too are also always soluble. The new ones comes in when we brings in the halides, the metal oxides, and then also all hydroxides are, what are they? All hydroxides are insoluble. So anything that contains this, so all hydroxides are insoluble, which is contains this thing, OH is insoluble. Except again, if they form with this people over here, then they are soluble. Because these things, no matter wherever they go, they are soluble. And 1, 2, 3, 4, 5. There are two more left. But what I would say is that the first two of the solubility rules are non-negotiable. But also sometimes there is something that we call complex ions. That is when an ion or a metal that can form many other bonds forms bonds with oxygen. Like for example, in hemoglobin, the hemoglobin, the ion in it forms a complex with the oxygens. That is why it can carry so many oxygen atoms, and it works like that. Now we're not going to go too much details into that. Just know that complex ions forms when there is this metal can form many bonds with most electronegative elements like oxygen. What's it? Hmm? Yes. So far, as you can see, most of the things that we've been doing has no. So as you can see, most of the things that we've been doing is just the understanding of it. None of these has formulas. None of these have calculations whatsoever. But now let's move to, the part that is high yield to the MCAT. This, you could get maybe like an objective question to pick from, but these ones are going to require you to work out, to work, one or two things. So the first thing that we're going to tackle over here is concentration. So concentration, and I know you've heard this before a million times, but when we say concentration, it is the amount of solute we have in a given solvent. That is just the concentration. And we can express this in so many ways. But then the ones that the MCAT focuses on about are percent composition, like alcohol, how they say an alcohol is 14% alcohol or 10% alcohol. It's just another form of concentration calculation. So a percent composition over here, right? It is also percent composition. Composition. It is just the total volume of the solute up here. So let's say when you go buy alcohol, the total volume of pure alcohol in it is like, say, 10 decimeter or 10 liters divided by the total volume of the solution. So of the entire solution, then you multiply that by 100%. So that is how.
So when they say this alcohol is 14%,
It just means the alcohol content in it is 14%.
so the composition is like 0.014?
No, it's still 14%. Can you play? Let's see. So, for example, if a brewing company makes an alcohol, they make an alcoholic beverage, but in that alcoholic beverage, they put, say, 10 milliliters of pure ethanol or pure alcohol into the solution, and then for this 10 millimeters, they put it into 100 milliliters of whatever solvent that they are using. The composition is going to become here the total volume of the solute, which is the 10 milliliters, divided by the total volume of the solution. So it's going to be 10 plus 100. Multiply by 100%. So in that case, we're going to have 10 over 110 times 100, right? And then from here, you could do the calculation. This one will be 11. If you do this one, would cancel this 1 over 11 times 100%. Right? So 1 over 11, however, it gives you, what does it give you? Yes. So then it like 9.09% alcohol percentage. So then you get your total alcohol percentage to be this in the drink. Pause it.
On my Zoom. I just got on my Zoom right now.
Now, this percentage composition is also used in calculating sometimes percentage composition of sugar, which they call bricks, or some other forms of, concentration calculation. But then there is another one which is called mass composition. So we have the mass composition. So the mass composition is the mass of the solute, once again, divided by the total mass of the solution. Now, if they want it in percentage, if there is like a percentage mass composition, then you multiply by 100%. And then you go that way. This and that work hand in hand. Then we have the mole fraction. The mole fraction. The mole fraction is also another way of we expressing a concentration. So the mole fraction of, let's say, a substance A is equals to the moles of A or solute A divided by the total moles of the solution. You see how it is always of the entire solution, but not just the solvent. Let me wipe this out of here. Right? It's always the entire solution, never just the solvent, because the solute makes part of the solution. Once again, from the mole fraction, we can go to molarity. Molarity. Now, molarity is my favorite.
Are you ready?
Molarity, right there.
Yeah.
This video, editing this video will be hell. So many breakages.
You're not doing it.
But then that person, you don't want to make
so
them suffer.
Sorry, Richard. That's what you're saying.
All right, so molarity over here is also equals to the moles of the solute, once again, divided by the volume of the solution or the solvent. This here could be the solution or the solvent because the solvent makes the liquid part of the solution, so of the solvent, and it's in liters, or it could be in decimeter cube. It works. And then we have molality. See how confusing it is. So there is molarity and there is molality. Don't get it confused. Don't get it confused. So the molality is once again the moles of the solute, on top part here, but then the down part here is the kilogram of solvent. In other forms, the mass of the solvent, but it should be always be in kilograms. So let me just say here the mass of the solvent, but it is always in kilograms. It's never in grams. So these 1, 2, 3, 4, 5 are different ways in which we can express. Yes, different ways in which we can express concentration. But then there are two more, which is not a way of expressing. Two more, which is not a way of expressing concentration, but it kind of fall in the way. And we've tackled this before. Normality. Something is normal. Normality. Now, when we talk about normality, let's say we have this compound over here. We've tackled this before, but H2SO4 over here. And we are dealing with acid and bases, and we want a proton donor. So that means we are interested in protons. So the normality is just the equivalence there. The equivalence of protons, the equivalence of the proton that we are interested in the compound. So over here, this can be deprotonated twice because it has 2 protons. So the equivalence of this is going to be 2 because it has, it can be deprotonated twice. So that is how the normality would come in. So the normality is going to be the moles of the substance we are interested in, divided by however we are comparing it to, divided by whatever substance we want to dissolve into. So it could be the volume, it could be the mass, it could be anything. So that would be it, divided by, say, it could be the mass, it could be the volume, it could be whatever. That is normality over there. And then what we have, what we call the dilution. Now, every high school student have seen this equation. Dilution is just, we put in more water or we diluting a stock solution, which the regular one, they say C1V1 equals C2V2. But then just this, the C1V1 here is just the concentrations. And concentration can be expressed in so many factors. So I just limit ourselves here. So it could be, for the MCAT purposes, it is M1, which the M is the molarity. Once again, it is what? The molarity. M1, and then we could say maybe V1 equals to M2 V2. However way you want to put it. So these formulas are just different ways of expressing concentration. And once again, concentration is just the amount of the solute that we have in a given solvent. Pause up.
Perfect.
All right. So the next part that we are on is the solubility equilibria. Now, we have discussed before, like the equilibrium of a reaction, the rate of forward reaction, reverse reaction, those things that we did in the previous chapter is basically here. What this thing is trying to say is that when you dissolve sparingly soluble, so we said over here, sparingly soluble does not fully dissociate in the solution. In a solute, it doesn't fully dissociate. So it goes little bit, then a little bit, then a little bit until an equilibrium has reached, and that equilibrium that is reached is what we call sparring solubility equilibrium. So, for instance, if we take a compound like silver chloride, right, AgCl, which is a solid, and then we dissociate it into silver plus and then chlorine minus over here, which this one are going to be in aqueous. This thing does not fully just dissociate into this. There is still going to be some level of silver chloride in the solution. So what we say is that if we are supposed to write the rate with which this is forming, we call it KSP, right? That is the solution solubility equilibrium, and is equal to, assuming that we have this as our sparingly soluble ionic compound. If this, let's say we have A, M, B, N. The reason why I wrote it here A, M, B, N is this is just the subscripts. If silver chloride has like a subscript over here, those will be the M and then the N. So if this dissociates to form something like A, N plus, and then you put the M here, dot N, B, M minus, because when it dissociates, the ions would cross and you have to make sure the equation is balanced. Then the KSP, P, this over here is always solid, is going to be A into brackets, the N plus M over here, dot the B into bracket, the M minus, then the N up here. Now, this can interchange. Just know where they go and what they mean. After that, however they go here, you can figure it out. So this is the equilibrium, the solubility equilibrium formula, right? You got to add it to your repertoire of formulas over here. After that, when we was doing the equilibrium constant, we said we had something that we call the equilibrium quotient. That will use the equilibrium quotient to determine where in the reaction that we was, whether we was close to completion or we was close to the equilibrium constant. Over here, its counterpart is called the ion product. So the ion product, which is IP, ion product. And once again, back then, we said the equilibrium quotient has the same formula as the equilibrium constant. The same thing over here, the ion product has the same formula as the equilibrium constant. Yes, so the KSP is equal to the ion product. The formula is the same. So you could just say the formula is basically the same thing. So let's say we want to write the KSP for the iron chloride. It is going to be this Ag.Cl minus over here. There is no and whatever, this is plus minus. This doesn't, it's not over there because it's 1 over here. Let me see if the iron chloride is true. Yes, that is how you want to write the equation of it. But then some preambles that you want to see is that if the KSP is equal to the ion product, the thing is at equilibrium. That means it is in a dynamic equilibrium. Into bracket, let me say the dynamic. It means the reaction has reached a point whereby the rate with which silver chloride is dissociating into this is equal to the rate with which this is forming back to silver chloride. Isn't it beautiful? But then if KSP is less than IP, right? That just means that let me go this way so it is much more better to understand. Let's say IP equals KSP is the same thing over here. But then if IP is less than KSP, that means we are not yet at equilibrium, not yet at equilibrium, right? And then the reaction will favors the forward reaction. Let me just use arrows, the forward reaction. So it means we are not yet at equilibrium where the rate with which we are going here is equal to the rate with which we're coming back. So that means we are favoring the forward reaction. We are going to be forming more of this and this. And if IP, which is the ion product, is greater than KSP, it just means that we have superseded the equilibrium. So we are above equilibrium, or we've reached beyond equilibrium, above equilibrium right here, which usually don't happen much, but it just means that the reaction now favors the reverse one, right? It's just a reverse reaction over here. So it means we are going to be forming more of the silver chloride instead of dissociating more of silver chloride. So that is the solubility equilibrium over there. Maybe let's come here and finish it up.
Baby.
Okay, let's finish it up. So for the point that we've reached what we call the common ion effect. What is the common ion effect? Now, this is something that I even need to brush up on it a little bit. But I think the general concept is that it links to the solubility equilibrium and the solubility constants over there. It's just that when you put a sparingly soluble solute into a solvent, you get some that are dissociated, and then they give you a series of values. So you're supposed to use that series of values to find your KSP or your ion product. But if you do know the formulas, that shouldn't be too difficult. So I'm going to jump over it and then do my research on it. But the next part that we are going is the colligative properties. Colligative properties. Now, when we say colligative properties, we're talking about of the solution. It's just that they are properties that does not depend on the chemical nature of either the solute or the solvent, but then the concentration, the concentration of the solute in the solvent. Those are the colligative properties. It's basically like that. And the first law that comes over here is what we call the Raoult's law. Raoult's law. So colligative property, they are just properties that depends on the concentration, on the conc of the solute, rather than the chemical property, rather than the chemical property. Now, there are a couple of colligative properties. We have vapor pressure depression. We have freezing point. We have boiling point elevation, freezing point depression. We have osmotic or oncotic pressure. Those are the colligative properties. Now, let's talk about it. The first one, the vapor pressure depression, is talked about in the Raoult's law. Very good name. I don't know the full name of the person. I refuse to do the research on the person this time. So we have a Raoult's law. Now, the Raoult's law states that the more of a solute you add onto the more of a solute that you do add into a solution, the more you decrease the vapor pressure.
There's an L in Raoult.
They will know, but I don't really care about the spellings that much.
And then the apostrophe?
It's at the where the T is. They know.
Okay, I never paused it, so you can just restate that idea.
Yeah, so the Raoult's law states that the more impurities, or let's say the more solutes you add into the solvent, the more you decrease the vapor pressure of the solvent. So it just basically means that the vapor pressure is inversely proportional to the number of solutes you add into the solution. Now, that would give us, say we have the vapor pressure of a substance A. The vapor pressure of substance A is directly equals to the mole ratio of substance A times the pressure of A. Let me see if this should be right. Yep. Times the partial pressure. Yes. Yes. So the Raoult's law states that the more of a solute you add into a solvent, the more you decrease the vapor pressure. So this right here is the Raoult's law formula. It means if we want to know the vapor pressure of A is equal to the mole fraction of A in the entire solution. And we already said the mole fraction over here, the formula is right over here, is multiplied by the partial pressure of A. That's the Raoult's law. Now I'm not going to go much details into it. And this determines what we call the vapor pressure depression. Now from the vapor pressure depression, we have boiling point elevation. We have the boiling point elevation. See, how is vapor pressure connected to boiling point? We know that a substance reaches its boiling points if the vapor pressure of the substance is directly equal to or a little bit above the ambient atmospheric pressure. So we decreasing the vapor pressure of the thing by adding more things, we are thereby increasing the boiling point because we are making it hard for us to gather enough pressure to meet the ambient atmospheric pressure for the thing to boil. So that is why when you add more things into a solvent, you decrease the vapor pressure, you increase the boiling point. That is basically what it is. But then, boiling point is just a temperature. So the formula that we work it out over here is that the change in temperature of the boiling point is equals to I. Now, I is what we call the Van Hoft factor. I'll come back to it, put a pin in it. KB, which is a constant of proportionality, right? Multiplied by the concentration, which is the molarity of the whole solution. So I could say MB over here. So once again, the change in temperature, well, the change in the temperature of the boiling point is equal to I, which is equal to the I is equal to the Van Hoft factor. How do we determine the Van Hoft factor? Let's say we have a compound, sodium chloride. Once again, sodium chloride is going to cry over here. Dissociating into sodium chloride plus chlorine minus. Since at the end, it gives rise to two species, the Van Hoft factor is just 2. So it's basically the number of species that becomes the solute. That is the Van Hoft factor. And this gives us the boiling point elevation, means the temperature is going to increase. Now, note that the temperature that you calculate here, it is not the boiling point of the solution. It is just the temperature change. So if you want to find the actual boiling point, you just have to add this temperature change into the actual boiling point of the solution in order to get your boiling point, the final boiling point. And then we have freezing point, the freezing point depression, right? The freezing point depression is the same formula as the boiling point elevation, just that the thing changes. So once again, I, a Van Hoft factor, K, instead of boiling, is supposed to be freezing. Now, this is a constant of proportionality and will always be given. This is the molarity times the molarity, right, of the substance, of the solution that we are working on. So it's basically the same, just a change in 1 or 2 terms over there. Now, once again, the temperature is freezing point depression means it's going to reduce. It is not the final freezing point of the solution. It is just the temperature decrease. So if you want to find the freezing point, you just have to, subtract this temperature from the actual freezing point. Now that is how when it starts snowing or when it's about to snow, you see the people I am putting salt on the road. It's basically because of this. When you have ice, when the snow falls, you have ice. Now ice is basically water, but frozen water, right? When you have ice like this and it is freezing, right, it will reach a point whereby the rate which the ice freezes, right, is equal to the rate which the water melts to become ice. Once again, and that temperature is 0 degrees Celsius for pure water or 273 Kelvin, depending on what you use. Now, if we add salt into the ice, the equilibrium point, the little water that is about to freeze into ice, the salt will dissolve in that water, decreasing the freezing point of it. So once it decreases the freezing point of it, now more water water cannot go into the ice form because the freezing point is now lower. You understand it? And but since the salt it was coming, it will absorb the heat that the water already have to dissolve in it, to break the bonds, right? More ice will be involved because of the Le Chatelier's principle. More ice will be made to convert into water to compensate for the water that has already lost its heat. And that means more ice would melt. That is why it is possible that we put salt on the roads when it starts snowing. That's basically it. It's just basically a colligative property of ice in salt solution. The last colligative property that I want to touch on is osmotic or oncotic pressure. Now, the osmotic or oncotic pressure, this is very important when it comes into, the human body and cell perfusion, or how, nutrients travel into our cells. This is where this becomes very much. We all know that water would move from a region where there is a higher concentration of it into a region where there are lower concentration of it, because the region where there are lower concentration, there are more solids, colligative property. So it is just a force between the suction or between these two boundaries. Where there are less water will suck more water to come in there. And that will be a colligative property of it. Now, the formula for oncotic pressure, which is given by this, I think it's pi or whatever, is equal to, let me see, I knew this off my head, but let me just, it's equals to, once again, I, it never change. I is just the Van Hoff factor once again. I, and then the molarity. There's a concentration of the solute. Let me finish. The molarity multiplied by R. Now, R is a constant of proportionality, just like Kf over here. It's a constant of proportionality times temperature. So this would always be given to you. This will be given. This will be given. And that gives us the oncotic pressure on about the colligative properties. So all in all, that is 90 to 98% of everything you need to know about solutions on the MCAT. We started talking about how ice pack and sweet tea works by exothermic and endothermic, whatever, giving heat. And then we went on to talk more about dissolving things and then the equilibria constants, and talked about the concentrations. And then we went on to solubility equilibria, where we discussed the ion products and then the solubility constants, and we came to colligative properties. So that is everything that I can recall top of my head that we do need to know for the MCAT. Thank you once again. If I miss anything and if I make any mistake, please, you can put it in the comment section and I will respond and I will make the corrections for myself. Thank you very much. See you in the next video. That's it, baby.